Okay, so now that we have an understanding of what centripetal acceleration is, let's look at the forces involved. So let's say I grabbed a bucket of water like this, and I started swinging it around over my head like this. This is a common physics demonstration you might see. You can probably guess what's going to happen. The water stays in the bucket. It's something you've probably seen or maybe experimented with in the past. And the question is, can we determine what the tension in that string will be? This is a useful thing to be able to calculate. There's lots of applications of this. So let's think about it. What we know is we know how to calculate centripetal acceleration. If only we had a formula that would relate acceleration to a force. If only. Well, we have Newton's magical second law, F net equals mass times acceleration. And that's still going to apply here if we're talking about the net force. Remember, this equation only applies if we're talking about the net force. So let's look at that bucket. Let's just draw a quick free body diagram of that bucket. Right? Bucket on its side like this, right? And the string is over here, is attached over here, right? So the question is, what are the forces acting on this bucket like that? I just drew it like as if it's like on the left side like that. So what are the forces acting on this bucket? Well, there's gravity for sure. And that would be pulling it down. But let's just ignore gravity for now. Let's look at the other forces that are applied to it. We'll get into why we can ignore gravity for now. We'll get into that later and how gravity comes into play. But for now, let's just ignore it. So what other forces are acting on this? We know it's got speed. It's spinning around, right? It's got speed, but there's no force acting in the direction of that speed. Another thing to keep in mind is we're going to assume it's moving at a constant speed along that direction. But what we do know is that when it's spinning in a circle like this, there's going to be an acceleration towards the center of the circle. And one thing about this equation, because technically it is a vector equation, right, where F net and acceleration are vectors, and the reason why that's important is because the net force always has to be in the same direction as the acceleration. So the acceleration, or the force from the string, the only force that's acting on it, other than gravity, is going to be towards the center of the circle as well. It has to be, right? And the other thing to keep in mind is it's a string, and we've talked about this before, how strings are only able to provide force in the direction of the string. So it would only be able to provide a force in that direction anyways. There's no other way that it can provide force. Can't provide any lateral force. So the only force really that we're concerned with right now acting on this bucket is just a tension force in the string. And that's what we're actually going to, I'm going to erase that. We'll call it a tension force. So we'll just call it capital T. Actually, you know what? That's confusing because T is what we used for period in the last one. So let's call it FT, force of tension. All right? So can we calculate this with the same formula? And we can, right? We just need to find our acceleration. We're given the mass in the question. It's a 1.5 kilogram bucket. But we can calculate our centripetal acceleration, right? Which we have a formula for. In this case, we're told that it takes 0.65 seconds for one rotation. So that's the period, right? That's our t value. So the equation that we can use for centripetal acceleration is, what was it? It's down here on the previous page, 4 pi squared r over t squared. 4 pi squared r over t squared, right? So we know 4 times 3.14 squared times the radius. The length of the string is 0.7 meters. And that's going to be all over the period, 0.65 squared. Right? And clearly here, if we look at the units, it's going to come out to meters per second squared. Squared times 0.7 divided by 0.65 squared. Oops, got to put the brackets in that. 0.65 squared. That comes out to 65.34 meters per second squared. So the net force, we know that's the acceleration, and that's the overall acceleration of our bucket. So that means the net force has to equal mass times that acceleration. And we know the mass is 1.5. Acceleration, we just calculated, is 65.34. So our net force should be 98.01. and that's newtons. So that's the net force. And since the only force that's acting on this bucket that we care about is the force of tension, right? That must mean the net force is equal to the force of tension, right? It has to be, because that's the only force. So it's just going to equal the force of tension. So therefore, the force of tension just equals 98 newtons to two significant figures. Okay? And again, we don't really give a direction here because the direction is going to be constantly changing as it moves around the circle. It's constantly in the direction towards the center of the circle. Okay? There we go. So that string basically needs to be able to support 98 newtons of force. All right. So next, I do the same demonstration, but I swing the bucket in a vertical loop. So picture I'm holding it out to the side with my arm out, and I'm swinging it around in a vertical loop instead, right? This is the center. This is the string attached to the bucket, right? In a vertical loop. So it's sort of going around the circle like that. So again, this is maybe a demonstration you've seen somebody do in the past, but if you do it fast enough, the water won't come out, right? You just got to do it fast enough. You got to have faith in the physics. So the question is, determine the tension in the string at its lowest and its highest point. So we're assuming everything's the same. The radius is the same. The speed that I spin it at is the same. We just want to know what the tension of the string is going to be at its highest and its lowest point. So that's at its highest point right there, and then also at its lowest point, right? What's going to be the tension in the string at each of those cases? We can call this, we'll call it FT1 for the highest point and FT2 for the lowest point. How about that? So, okay, how is this any different than the previous question? We said all the values are going to be the same. So let's ask ourselves, is the centripetal acceleration going to be the same, first of all? Is it going to be the same? Well, let's think about what's involved. The radius and the period. And I said, let's assume I'm spinning it at the same speed. So if that's the case, we know the centripetal acceleration is going to be the same. So 65.34 meters per second squared. So that's the same. We need to find the tension at the top and the bottom. And to do this, maybe let's draw a free body diagram of the top and the bottom. So let's look at the bucket when it's at the top first. When the bucket's at the top, here's our bucket. We have a string that's coming off the bottom, right? The string that's coming off the bottom. Let's just label this. This is at the top of the cycle. So what forces do we have acting on this bucket? Well, in this case, we have the tension, right? The tension definitely is pulling down. It's always pointing towards the center of the circle for the centripetal force. So we would call this FT1, right? We said that's the one from the top. Are there any other forces that are going to matter here? Well, this time, because we're doing a vertical loop, gravity is going to come into play, right? While this thing is up in the air, sort of up at its highest point, gravity will come into play because the bucket has some gravity, right? Or it has some force of gravity applied to it because it has mass. So in this case, we are going to include the force of gravity. By the way, the reason we didn't do it up here, another reason why we didn't do it up here is because the force of gravity is not in the direction of the centripetal acceleration. It's like downwards, it's out of the plane. So that's why we're not worried about it here. But in this case, we might as well, we have to include it because it's in the same direction as the tension or the centripetal acceleration. So we have to include it. So that's interesting. We have a force of tension pulling it down. We also have a force of gravity pulling it down. So what can we do here? Well, we know, like, is this going to change? Is this net force going to change? The mass of the bucket hasn't changed. And the acceleration is constant. Doesn't matter where on this loop it is, it's constant. So isn't the net force still going to just be equal to 98.01 newtons? It is, right? I'm leaving the 98.01 newtons because I want to keep extra significant digits until our final answer. So that's still going to be true, but what's happening here? Well, these two forces are going to have to combine to give us this net force, right? Because that net force is like the combination of all the forces acting on it. So this is our net force here, and that's based on our acceleration. So we know that the net force is going to equal our force of gravity plus our force of tension 1, Ft1, right? So we know our net force, we know our force of gravity, or we can calculate it. Let's just actually calculate that super quick. It's just going to be 1.5 times 9.81, which is 14.72, right? And, you know, we know those two things, so we can just solve for the force of tension. Oops, let's use blue. So the force of tension is going to be F net minus the force of gravity. So what's that going to give us if we do that? It's going to be 98.01 minus 14.72, which gives us, minus 14.72, which gives us 83.29 newtons. So that seems to be the tension at the top, right? While this thing is spinning around, so that's the tension at the top. That makes sense. The question is, what's going to be the tension at the bottom? And make a prediction here for yourself. Do you think it's going to be a higher value, a lower value, or do you think it's going to be the same? Well, only one way to find out. Let's start off by drawing a free body diagram of it when it's at the bottom. So when it's at the bottom, the bucket's going to be like this, and we have our string this time pulling up, right? So again, we know our tension force is going to be upwards because, you know, when it gets to the bottom, you're like basically lifting it up as it goes around. So this is our Ft2. And we also have a gravity here at the bottom, right? And the gravity this time is going to be pulling it down with that same force of gravity, which is 14.72 newtons. So we know at the bottom the net force is going to be the same because the acceleration is the same, right? And the mass is the same. So our net force on the bucket, that's not changing over time. So that has to be the same. But if we do the equation now, F net equals, well, let's look here. We have our Ft pulling up and our Fg pulling down. They're pulling in opposite directions. So we have to be a little bit careful with this equation now. What I'm actually going to do is I'm going to define a positive direction as up. And we should always define a positive direction. I know I didn't do it in the previous one. But in the previous one, we were basically assuming that the positive direction was down because we plugged these all in as positive numbers. So let's assume this time that the positive direction is up. It's usually the way we do it. So if that's the case, the F net is going to be equal to Ft2 minus Fg, right? Because Fg is in the opposite direction. So we're basically manually making that negative because it's downwards. So let's see what happens when we solve for T2 this time. It's going to be F net plus Fg. So if we do that calculation, it's going to be 98.01 plus 14.72, which is going to give us 98.01 plus 14.72 is 112.73. And that's our Ft2. So it ended up being bigger. And that makes sense because when it's the bottom, gravity is like pulling against that tension, right? But when it's at the top, it's like the bucket is lighter because, you know, gravity is working in your favor. It's pulling it down in the same direction as the tension. So that makes sense. Lastly, let's just round these to two significant digits each. Ft1 is equal to 83 newtons, and Ft2 is equal to 113 newtons. Okay? So hopefully that makes sense to you. So if you do a little bit of manipulation with the equations, if you realize, you know, we just said in the previous question, what we did is F net equals mass times the centripetal acceleration, right? But if you do a little bit of algebra with that. Remember, we defined centripetal acceleration as v squared over r, right? So if we just do a substitution here, v squared over r instead of this a, right? What are we going to get? We're going to get mv squared over r, right? That's it. And when we have this, when we're doing this, in terms of the centripetal acceleration, what we can do is we can decide to call it, instead of F net, we can just call it FC for centripetal force. So this is the force that's centripetal. One thing to keep in mind, though, this is very important, is that this centripetal force is the net force. And that is very important because it's easy to think that that's just like another one of the forces that act on the object. But no, if the object is moving in a circular motion, the centripetal force is the net force. It has to be experiencing that net force to move in a circular motion. And the other thing just to keep in mind is that this equation is useful when you're given the speed, right? The speed that is traveling. Otherwise, if you're given the frequency or the period, then you're going to have to go back and calculate the acceleration with these equations and plug it in to F net equals ma, right? But either way, it's not too hard. This is just like a shortcut way to find the net force on an object when you're given the speed. So a 1,200 kilogram car is traveling on a highway at 100 kilometers per hour. It goes around a circular bend with a 600 meter radius. You should realize this is the very similar question to the one we did back here on this page, example 1. Same question, but now we want to know the force, right? So we have a car traveling down the road, and let's just draw a quick sketch again of this. So the radius of this curve is 600 meters, right? And we know the car, this time we're given the mass of the car. Notice you need the mass to be able to find the force. And we know the speed of the car is 100 kilometers per hour. And if you remember from the last one, that comes up to 27.78 meters per second. Okay, is for the speed. So that's all we need, right, to be able to calculate the centripetal force. So it's just mv squared over r, where the mass is 1,200 kilograms. V is 27.78. Square that all over the radius, which is 600 meters. By the way, if we do a little bit of unit analysis here, we should see that this is in kilograms, so it's going to be kilograms times meters per second squared all over meters. So this is going to be squared and squared, right? That's going to cancel out with that, and we end up with kilogram meter per second squared. Which, hopefully you remember, that is what a Newton is defined as. It's a kilogram meter per second squared. So our units check out, basically. Okay, 1,200 times 27.78 squared divided by 600 gives us a force, a centripetal force of 1543. Or, to two significant digits, 1,500 newtons. Okay? So that's a centripetal force. What does that mean, though, for this car driving down the highway? Well, to make it turn around this corner, it needs to experience this force. And what direction is the force going again? It's always towards the center of the circle. Right? So if we look at this from a different view, let's look at this from the car from behind. Right? Here's the car, here are its tires on the road, right? The direction of this force is got to be towards the center of the circle. It's like out the right side of the car if we're traveling on the road. This is, by the way, this is looking at the car from the back. These are the tail lights. Here's the top of the car and the window. Hopefully you understand my drawing of a car. So this is 1,500 newtons, like towards the inside of the curve, right? What's actually providing this force? Well, the only thing that's actually contacting the road are the tires. So the tires are actually the things that are providing this force, right? So they, in addition to providing grip on the road in like the forwards and backwards direction, in order for a car to go around the corner, it needs to provide this force towards the inside of the curve, right? What happens if this force disappears? What happens if the and by the way, we call this a friction force, right? It's the friction force between the tires and the road. What happens if this force were to all of a sudden disappear? What would happen to the car? If your car lost traction with the road? Well, it would stop going around that corner, right? It would continue going in a straight line. The friction on the road needs to be there at that force to allow it to continue to turn. If that disappeared, it would go in a straight line. And that's the same with the bucket questions, right? If you all of a sudden snip the bucket would try to move in a straight line in the direction it was going when that cord was snipped. Okay, so last question. Looking back at example 5, so the one that's right here. What's the slowest speed the teacher could swing the bucket so that the water doesn't fall out at its highest point? So we're swinging it around, If I do it too slowly, there's going to be a point where the bucket just like sort of falls straight down, or the water falls out of the bucket, right? And it's asking what the slowest speed that can happen at is. So it's going to be at the top, right? So we'll draw a free water diagram again of the top, the bucket at the top of its sort of spin, right? So this is at the top, the string is pulling it down. So what do we know about the bucket that we can't change? Well, we know we can't change the force of gravity, right? We know that there's going to be a force of gravity pulling it down. What was the value there? 14.72 newtons. Now, is this net force going to stay the same as 98.01? Well, remember, the net force is dependent on the speed the bucket is swinging. So if we slow down the speed, as the question asks, what's going to happen to the net force? Well, if we look, speed is proportional, or the force is proportional to the speed squared, right? So as we decrease the speed, the force is going to also decrease, right? So the force isn't going to be this because we're slowing it down, right? So the force should actually be less. The net force should actually be less than that, the centripetal force, right? And we're trying to find the minimum net force possible because we're trying to find the minimum speed possible. So if you think about it, what do we want to happen at this highest point? What do we want this force of tension to be at this highest point? Well, remember, we're trying to minimize the net force, and the net force is going to be the sum of these two things. So to minimize the net force, we need to get rid of this tension force. It's like, if you think about it, if you're swinging this thing around, you swing it so slow, so at the top of its swing, it's like barely, the rope isn't even pulling it down anymore. It's just sort of making its way over as if it were being tossed through the air. And that's what we want. We want this force of tension to be 0 at the very top. And then as soon as it starts coming down again, the tension will start to increase again. But at the very top, just at the very peak, we want the tension to be 0. So if this is the case, we know the only force acting on this bucket is going to be the force of gravity. So the net force is going to be 14.72 newtons. And if we know the net force, can we figure out the speed based on this? Well, we can, because remember, the net force is the centripetal force. The centripetal force is the net force. So this is also the centripetal force, which is equal to, what does it equal? mv squared over r. Right? So we know, and we're trying to solve for v here, right? So I can rearrange this equation. If I do v equals the square root of fc times r over m, right? So if we do that, oh, I hate writing in red. I meant to write in blue. That's okay. So the speed is the square root of 14.72. The radius doesn't change, right? What was it? The radius was 0.7 meters. And that's all over m, which is 1.5 kilograms. So if we do that calculation, square root of 14.72 times 0.7 2.62, so 2.6 to 2 significant meters per second is the slowest speed we would need to be able to make it still pass just over the top. with zero tension in the rope at that very top. So we should be able to make it all the way around with 2.6 meters per second. You'd be pushing it. You'd probably want to do it a little bit faster than that, just to make sure that you don't get wet. But theoretically, that is the slowest speed that you could do it at. Just to compare quickly, what was the speed in this question? We never actually had to calculate it, right? But if we do a quick calculation, we know the net force was 98.01, right? So we can just do that same calculation that we did down here to find out what the speed was in this case. And so it's going to be the square root of 98.01 times 0.7 divided by 1.5. So that speed was 6.7 or 6.8 meters per second in this case. So in order to get these forces, it was much faster, 6.8 meters per second. But this is the slowest speed you can theoretically make it around. All right, there we go.